Most engine manufacturers agree that 40% of all diesel engine failures are a result of poor cooling system maintenance or neglect. A heavy-duty diesel can generate excessive engine temperatures. If the heat is not transferred, engine components will build up excess heat that can cause severe damage to the engine. A properly maintained cooling system can help dissipate as much as 30% of the heat generated by a diesel engine. The cooling system in a heavy-duty diesel is a closed-loop system consisting of 6 major components: the water pump, the coolant fluid, the flow channels, the thermostat, the radiator, and the coolant filter. The water pump generates the flow of the coolant fluid through the flow channels of the cooling system. The coolant is routed through the engine block and around the cylinder walls and heads. This reduces the heat created by combustion and the friction created by moving parts. The coolant fluid, which is a mixture of antifreeze and water, then travels to the thermostat where it is directed to the radiator for cooling or sent back through the system for another cycle. A portion of the fluid passes through the coolant filter where debris and combustion byproducts such as coarse sand, rust, and scale are removed and contained. Other components that rely on the cooling system are heater cores, oil coolers, and aftercoolers. Protecting these components is critical in keeping heavy-duty diesel engines operating in extreme temperatures. A properly maintained cooling system is important in protecting these engine components against cavitation erosion, corrosion, rust, and scale, which can cause reduced heat exchange and lower engine efficiency. Cavitation erosion results in the pitting and wearing out of the cylinder liners. During all cycles, the engine piston experiences side blows from the connecting rod as it moves side to side to rotate the crankshaft. These side blows, commonly called piston slap, cause vapor bubbles to form next to the liner. As the liner moves back toward the coolant, the vapor bubbles implode on the inside surface of the liner. This causes a scouring or drilling action known as cavitation erosion. Cavitation erosion can occur in as few as 250 hours or 12,000 miles. If left unchecked, this erosion will perforate the liner and cause coolant to enter the lubrication system, resulting in costly repairs. Cavitation erosion can also damage the water pump. Air bubbles burst against the surface of the impeller, gradually wearing the impeller away. This diminishes the pump's output and performance. Another common problem in a poorly maintained cooling system is corrosion. Corrosion appears in the cooling system in several forms: as oxidation on aluminum components, as solder bloom on the surface of the radiator, heater core, and oil cooler, as rust on cast iron fluid channels, and as scale buildup. Oxidation and solder bloom appear as a white powdery substance caused by the corrosive action of combustion byproducts introduced into the system. These byproducts increase acidity in the system, which lowers the pH and can cause rust. When an engine is started, the small particles of rust are flushed away, but the larger ones remain. These stationary particles are then subjected to heat, which solidifies the particles to form scale. These scale deposits act as insulators, creating engine hotspots. 1/16 of an inch of scale buildup has the same insulating factors of a 3¼ inch block of cast iron. Scale buildup can lead to cracks in the cylinder head, even with sufficient coolant in the system. Water alone is not recommended as a coolant. To protect system components, antifreeze is added to water to form a coolant mixture. There are 2 types of antifreeze: conventional and organic acid. Conventional antifreeze is usually made up of ethylene glycol or propylene glycol. Conventional antifreeze also contains inhibitors composed of neutralized inorganic salts, such as phosphates, which control the acidity or pH in the system, and silicates, which protect aluminum components against corrosion. Organic acid antifreeze is also usually made up of ethylene glycol, but contains inhibitors composed of organic salts, which contain no phosphates or silicates. These organic acid inhibitors, which protect the cooling system against rust and corrosion, allow for extended service intervals. There are 3 basic types of organic acid antifreeze: OAT, or organic acid technology, is an ethylene glycol-based antifreeze containing no phosphates or silicates. OAT contains organic salts, which are slow-acting, long-life inhibitors. However, due to the nature of the chemicals used, it can attack certain seal and gasket materials and therefore should only be used in applications approved by the original equipment manufacturer. Hybrid OAT, or hybrid organic acid technology, is a hybrid antifreeze composed of conventional technology, which contains inorganic salts, and OAT technology, which contains organic salts. Hybrid OAT offers the best protection of both technologies. Nitrided OAT, or nitrite organic acid technology, is an antifreeze composed of organic acid technology with nitrites added as extra insurance against liner pitting and flash rusting. To help antifreeze protect engine components against cavitation erosion, corrosion, rust, and scale, supplemental coolant additives, or SCAs, were developed. SCAs, which are a combination of phosphate, nitrite, molybdate, borate, and other chemicals, produce a molecular coating that converts decaying metals into a hard protective surface. Some types of conventional antifreeze already contain SCAs. This type of antifreeze is referred to as fully formulated and does not need to be pre-charged. Other types of conventional antifreeze do not contain SCAs and need to be pre-charged before using. SCAs are also added to replenish conventional antifreeze when chemicals drop below desired levels. Some antifreeze manufacturers approve mixing conventional antifreeze and SCAs with organic acid technology, OAT, or nitrided OAT antifreeze. This can alter the chemistry of the antifreeze, resulting in the need for adjusted maintenance practices. Check with the antifreeze manufacturer for mixing and maintenance recommendations. Hybrid OAT requires SCAs to be added when chemicals drop below desired levels. However, the chemicals will not deplete as quickly as they would in conventional antifreeze. SCAs contain inhibitors that prevent cavitation erosion and corrosion, polymers that keep hard water scale from depositing on engine surfaces, buffers that prevent acid formation in the coolant, and anti-foaming agents that reduce the vapor bubbles formed by air in the system. When selecting an SCA, it is important to choose products that have met standards set by the American Society for Testing and Materials, ASTM. The ASTM has specific tests for SCAs, including the D1119 test for ash and the D1384 test for corrosion in glassware. Your supplier should have test results for their products on file. SCAs do a tremendous job of protecting your cooling system. However, engine byproducts wear and tear from starting and stopping, and liner movement will deplete the SCAs. To keep SCAs at their proper level, you should follow the engine manufacturer's recommended service interval and adhere to a regular maintenance schedule. Along with SCAs, a properly installed coolant filter will help ensure a cleaner cooling system by removing impurities such as sand and rust from the coolant. Choosing the right coolant filter is an important part of maintaining your cooling system. See the Filter Types section to learn more.